In 2002, Dr. Bennett Amalu examined the brain of Steelers center Mike Webster, who showed severe behavioral changes after enduring countless hits during his football career. Webster's extreme actions, such as urinating in his kitchen oven and using a taser on himself, revealed a deeper problem. Webster died at 50, but Dr. Amalu noticed his brain autopsy looked far older. What had happened to him? Dr. Amalu made a startling discovery, a disease never previously identified in football players. The condition was known as chronic traumatic encephalopathy, or CTE, and is the first hard evidence that playing football could cause permanent brain damage. Currently, many researchers have used football to study the link between concussions and CTE to better understand the symptoms. CTE is a degenerative brain disease caused by repetitive head injuries such as concussions or traumatic brain injuries. Our neurons are the brain's building blocks. The axon, like an electrical wire, sends signals between neurons, but its length causes challenges such as fragility and hindering chemical distribution. The microtubules inside neurons help overcome these challenges by facilitating material transport throughout the cell. A special protein called tau keeps the microtubules together by sticking to the tubes outside. However, when microtubules break down, tau misfolds and detaches, leading to cell dysfunction and death. This misfolding can spread to nearby cells, resembling prion behavior. In conditions like CTE, abnormal tau buildup in neurons and astrocytes causes neurofibrillary tangles, NFT, impacting brain function. There are 4 stages of CTE, with stage 1 and 2 being considered low CTE and stage 3 and 4 being diagnosed as high CTE. Stage 4 is the most severe stage, normally associated with dementia. Although the process begins focally, it gradually spreads to involve widespread regions of the brain, including the frontal and temporal lobes, medial temporal lobe, diencephalon, and brain stem. The anatomical slice pictured in the top row shows a normal brain. The bottom row shows the brain of former college football player Greg Plotz, who died with dementia at age 66. His brain revealed atrophy and ventricles much larger than normal, which are circled in red. This figure illustrates p-tau pathology in CTE. Low CTE, p-tau is found in focal cortical lesions. High CTE, widespread p-tau is found in medial temporal lobe, diencephalon, plus cortical lesions. On the top row, positive tau immunostained tissue appears dark brown. Stages 1A is a college player, and stages 2 through 4 are former NFL players, with 4 being most severe. Stage 4 in the top row shows multiple cortical lesions, widespread neurofibrillary degeneration, and with the asterisk, it shows degeneration in the amygdala and entorhinal cortex. On the bottom row, positive tau immunostained tissue appears dark red. In stage 4D, there are large NFT around the vessels. The open triangles indicates immunoreactive astrocytes, which may be evidence of neuronal loss. This 85-year-old male, a former elite football player, exhibited signs of dementia prior to death. His MRI results showed global atrophy. In A, you can see the atrophy in the frontal and temporal lobes, and in B, you can see atrophy in the bilateral medial temporal lobe, which are circled in red. So why does CTE matter? Sports-related brain injuries are rare but can be deadly, making them the leading cause of sports-related deaths. Athletes in contact sports face CTE risks, leading to depression, suicidal tendencies, and dementia. At the present time, CTE can only be diagnosed at autopsy. Thankfully, the Concussion Legacy Foundation, spurred by Mike Webster's case, advocates for athlete safety through education and innovation. Though CTE lacks treatment, prevention is possible. Sports organizations should commit to more research about this topic for the prevention of CTE in future players.